In section 6.3, we're going to talk about conditions for parallelograms. Now, you have learned to identify the properties of parallelograms. Now you will be given the properties of a quadrilateral, and we'll have to tell if that quadrilateral is a parallelogram. To do this, you can use the definition of a parallelogram and the conditions. Basically, what you are doing is taking what you learned in 6.2, and you're doing now the converse of that. So now you're going to prove something is a parallelogram based on information about a quadrilateral. So here they are. Here are all your conditions. We know that if one pair of opposite sides of a quadrilateral are parallel and congruent, so if we know we have a quadrilateral and one pair of sides are parallel congruent, then it's a parallelogram. If we know that both pairs of opposite sides are congruent, then it's a parallelogram. If we know that opposite angles are congruent, then we know that the quadrilateral is a parallelogram. And here are a couple more. If an angle of a quadrilateral is supplementary to both of its consecutive angles, that's important. It's not just one. So for example, if you have x here, and it's supplementary to both this consecutive angle and this consecutive angle, then it's a parallelogram. And lastly, if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. Now I've given you 5 things. You only need to prove one of those 5 in order for you to prove if something is a parallelogram. So in example 1, I'm giving you this quadrilateral, and I want you to prove to me that it's a parallelogram. So, my laundry's done. Alright, I'm back. So now we want to prove that this is a parallelogram. So all we do is plug in all 4 sides and find out their lengths. And if you plug in 7 for x and 4 for y, you would find out the opposite sides are indeed congruent, and therefore, because opposite sides are congruent, we know that it is a parallelogram. In the last example here, in B, we want to show that this quadrilateral is a parallelogram, letting us know that Z is 11 and W is 4.5. Now, because we're only given consecutive angles here, we're going to prove that the consecutive angles are going to be supplementary. So we're going to plug them in. If we plug in these values, you will realize that the measure of angles F and H are both 118, and the measure of angle G is 62 degrees. And therefore, we know that since angle G is supplementary to both angle F and angle H, then quadrilateral EFGH is a parallelogram. Now, it's also important to notice that just because the 118 are the measures of angle F and H, and we know that opposite angles are congruent, we can't figure that out, and we can't use that to prove it's a parallelogram because we don't know the measure of angle E. If we did, then we could also say it's a parallelogram for that reason. In example 2, I want you to determine if each quadrilateral must be a parallelogram. Justify your answer. And do this yourself. So take a couple minutes, look at this, and determine if it's a parallelogram. If you did it correctly, the first one would be no, because you only have one pair of opposite sides parallel, and then a different pair of opposite sides are congruent. These are not conditions that would make something a parallelogram. And B, yes, because the diagonals bisect each other. So therefore, the quadrilateral is a parallelogram. So in example 3, you're going to show that quadrilateral ABCD is a parallelogram by using the given definition or theorem. So you are given these 4 points, and you are supposed to prove that this is a parallelogram based on the definition of a parallelogram. So, the first thing we have to do is graph it. So here's our graph. Now I want to make a note here that in order to prove that this is a parallelogram, you have 5 options, plus the definition of a parallelogram. You can either prove that opposite sides are parallel. That's the definition of a parallelogram. So that's what we're going to do, is prove that these are parallel. Opposite sides are parallel. But you could also prove that one pair of sides that are opposite of each other are parallel and congruent. So you could actually, for example, find the slope of segment BC and segment AD, and then use the distance formula to prove that they are congruent. That would also work. So let's find their slopes. So I already did that for you here, and you could find slopes by subtracting, using the formula for slope, or just counting. But you will notice that opposite sides indeed have the same slope. Therefore, because they have the same slope, they are parallel. And by definition of parallelogram, this shape is a parallelogram. You will be asked on a test or a quiz to prove that it's a parallelogram, or whatever other shape we're talking about, by using and by explaining what you're doing. All right, in example B, here are your 4 points, and it doesn't tell you how you're going to prove it. So here's your graph, and we could do the exact same thing in part A, the exact same thing. But I'm not going to do that. I want to prove that opposite sides, that one pair of opposite sides, have the same slope, and if we use the distance formula, would have the same length. Let's start with the slopes of segments GH and FJ. So GH, well, it looks like I go up 1, 1, 2, 3, 4, 5, 6. Up 1 over 6. So it looks like both of those have a slope of 1/6. So we know that one pair of opposite sides are parallel. Now, if I find the lengths of each of these, GH would be, let's see, 3 minus 2 would be 1 squared, plus 4 minus a negative 2 would be 6 squared. That would give me 36 plus 1, which would be the square root of 37. FG, if I subtract my, let's do y's, negative 1 minus a negative 2 would give me 1 squared. 2 minus 4 would give me, actually that'd be negative 4 here. So 2 minus negative 4 would give me 6 squared, and that would also give me the square root of 37. So because opposite sides, one set of opposite sides have the same slope, they're parallel. And since GH is equal to JF, the lengths are congruent, so therefore it is a parallelogram. So you have learned several ways to determine whether a quadrilateral is a parallelogram. You can use the given information about a figure to decide which condition is best to apply. Now once again, and I've already said this, to show that it's a quadrilateral, to show that it is a parallelogram, you only have to satisfy one of these conditions. So here's what you learned today. By definition, you know that both pairs of opposite sides are parallel, or you can say one of these 5. One pair of opposite sides are parallel congruent, both pairs of opposite sides are congruent, both pairs of opposite angles are congruent, one angle is supplementary to both of its consecutive angles, or the diagonals bisect each other. Any of those would be acceptable to show that a quadrilateral is a parallelogram. Our last example. In a parallelogram mount, there are bolts at each of these points, PQ, R, and S. Now, we know that PQ is equal to RS, and QR is equal to SR. The frame PQRS moves when you raise or lower the binoculars. Why is PQRS always a parallelogram? So it's saying, as you move everything on these bolts on P and A, and for example, if you move this part down and this part up, why would this yellow parallelogram always remain the same? You would say this. Because when you move the binoculars, the angle measures change. The angle measures, the diagonals, they would all change. However, the lengths of PQ, QR, RS, and SP always stay the same. So it's always true that PQ will always be equal to RS and QR is always equal to SP. Since both pairs of opposite sides of a quadrilateral are congruent, PQRS will always be a parallelogram. And this is what I am saying. You are going to have to be able to explain to me why things would be a parallelogram, and then prove it to me mathematically if you were given points of such, like in example 3.